So we have been talking about standardizing the way microprocessor access to the I/O peripherals. But how does microprocessor access to I/O devices to begin with? There are two ways a microprocessor can access to I/O devices. The first one is what we call memory map I/O. The access to the I/O devices is done exactly the way the microprocessor access the memory. The other one is what we call port map I/O. The access to I/O is done in a separate dedicated addressing and line and different protocol altogether compared to memory access. For memory map I/O, it is possible because there is no fundamental difference between memory and I/O. In all literature, memory itself was considered I/O. It is outside of microprocessor and it is still outside of microprocessor, but nowadays it is considered special and not I/O. In this scheme, micro-P considered I/O exactly like memory. The timing access is memory time access, if you still recall our topic on memory access read and write. The instruction used are also memory instruction, like store and load. For example, for the system in this diagram, when the address is 1111 at the MSB side, and the lower bit address we can ignore. When this 4-bit MSB are 1, the output of this AND gate will be 1, and inverted it becomes 0. This means the main memory is not selected. It won't be connected to the data line or the address line. And at that time, when the output of the AND gate is 1, it is actually selecting the I/O controller. When these are not all 1, the output is 0, inverted, then it becomes 1 here. At that time, main memory is selected, not the I/O controller. But the rest of the line, the lower address bit, and the data bus and the control, they are all share the same thing. Next is port map I/O. In this scheme, the microprocessor treats the I/O as a separate connection. The instructions used are I/O specific instructions. For example, if memory has store and load, the I/O has out and in. It also has separate address bus in use, but data normally will be the same, and the timing also will be different. The protocol and everything will be different. For example, we can look at this diagram. The main memory will have its own address line. I/O has its own address line, but data and control bus will be going to each of them, but coming from the same source. So that was the way to address the I/O devices. It is the way to find where the I/O devices are. Now, how to speak to them? There are a few strategies. Fundamentally, or the conceptual way of doing communication between micro-P and I/O devices, there are three ways. The first one is very manual. We call it program I/O. User code enters polling loop or await loop to check the I/O status. Interrupt. So in this one, instead of the program waits for the device to respond, now the program can continue, but the I/O device will send interrupt signal to the microprocessor so that something can be done. The third one is considered the most efficient, direct memory access, or in short we call it DMA. In this case, the I/O devices are given the control over the data bus. It is sort of the microprocessor or the entire motherboard system is opening a gate to the I/O device to access to the main memory system. Let us look at the program I/O first. User program will send data, then manually go into a polling or waiting loop to get the response. This is done by the code, most likely the assembly code written by the programmer. And the next instruction will only be executed after the response comes. So obviously, this is a slow process because of the wait cycle. For example, we can see in this flowchart. This flowchart is showing an example on reading from I/O, but the same scenario can be understood for output process as well. First, the microprocessor will issue a command telling that it wants to read something from the I/O device, giving the address and everything, and then it read the status. If the status says that the data is ready, then it will go and read. Otherwise, it will be looping to read the status. Until the status is okay, which means the data is there available for the microprocessor, then the microprocessor will read the data. And of course, the data that is read need to be kept somewhere in the main memory. And maybe that round just now is not complete. Let's say we want to read 100 byte, but in one run just now we only read 1 byte. So we need to repeat 100 times to read 100 byte. So this wait and this loop is causing program I/O to become a slow process. Next is interrupt I/O. In this scheme, the user or the program will set up for read and write, like the address and everything, tell the I/O device that it wants to read or write, then continue execution to the next instruction without waiting. It's then the responsibility of the I/O device to tell either the data is ready or not. Meaning when the I/O device is ready, it will send an interrupt. Then the micro P will attend to that interrupt in an interrupt handler. There is no time wasted waiting for I/O device. We can visualize using this flow snippet. At some point, the program will set up the I/O, like request, address, everything, and then it continue. And at some point, there is interrupt signal coming from the I/O device, and then after that, the execution of the assembly line or the opcode will go to the interrupt handler, and then whatever the program needs to do to get or write the data to the I/O device is done in that subroutine. And then it returns and then continue with the next instruction.